What if the universe has been trying to talk to us this whole time? Picture this: waves of light, traveling for centuries, carrying secrets from civilizations we can't even comprehend. Somewhere out there, hidden in the static between stars, could be a message meant just for us. This isn't science fiction anymore. Right now, scientists are decoding the cosmos, searching for patterns in the noise, listening for whispers from worlds beyond our own. And today, we're pulling back the curtain on 28 of the most extraordinary ideas pushing interstellar communication into the future. Think about how far we've come. Just a few centuries ago, we believed the stars were fixed points of light, silent and unchanging. Now we know better. Every flicker, every pulse of radiation could be a clue, a cosmic hello waiting to be deciphered. From the earliest attempts to interpret starlight to today's laser-powered transmissions cutting through the void, humanity's quest to connect with the universe has been nothing short of breathtaking. But here's what really sends chills down your spine. We're only just beginning. The methods we're developing now could one day crack the code of an alien language, or even reveal that we've been part of an interstellar conversation all along. So why does this matter? Because deep down, this isn't just about science. It's about something far more profound. It's about answering the question that has haunted us since the first humans looked up at the night sky. Are we truly alone? Every signal we send, every message we strain to hear, is a step closer to rewriting our place in the universe. And that's what makes this journey so exhilarating. Whether it's ancient light carrying echoes of distant worlds or futuristic tech beaming our presence into the cosmos, these 28 concepts are more than just theories. They're the building blocks of humanity's next great conversation. So buckle up. By the time we're done, you'll never look at the stars the same way again. The Arecibo Message wasn't just a random shout into the void. It was humanity's first carefully crafted cosmic handshake. On November 16, 1974, a team of scientists pointed the massive Arecibo radio telescope toward a cluster of stars 25,000 light-years away and unleashed a 3-minute burst of radio waves carrying a very special payload. This wasn't ordinary static. It was a pictorial message painstakingly encoded in binary, featuring everything from the numbers 1 through 10 to the chemical building blocks of life. Imagine drawing a self-portrait and launching it into the ocean, hoping someone on the other side might recognize it as a greeting. That's essentially what we did with the stars. The message contained some clever design choices. Scientists included a simple depiction of our solar system, highlighting Earth's position, along with a double helix representing DNA. Perhaps most charming was the crude stick figure of a human, as if we were saying, "This is what we look like, more or less." Of course, by the time this signal could potentially reach its destination, humanity might look completely different, if we even still exist. That's the fascinating paradox of interstellar communication. We're sending messages across timescales that dwarf human civilization itself. This bold experiment sparked intense debate that continues today. Some researchers argue broadcasting our existence could be dangerous, like a child calling out in a dark forest without knowing what might answer. Others counter that any civilization advanced enough to detect and decode the message would already know we're here through our accidental radio leakage from TV broadcasts and radar signals. The real brilliance of the Arecibo Message wasn't necessarily in its content, it was the proof of concept. For the first time, we deliberately structured information meant for alien comprehension, creating a template for future attempts. What makes this message particularly poignant is its timescale. Traveling at the speed of light, it won't reach its target star cluster for 25,000 years. If by some miracle it's intercepted and answered, we wouldn't receive a reply for 50,000 years. That staggering timeline forces us to confront an uncomfortable truth: interstellar communication might be less about conversation and more about leaving a cosmic message in a bottle for future civilizations to find. Yet the very act of sending it changed how we view ourselves in the universe. We stopped just listening and started speaking, however faint our voice may be against the interstellar background noise. While the Arecibo Message was a one-time experiment, a growing movement believes we shouldn't just wait for aliens to find us, we should be the ones reaching out first. This is Meti messaging extraterrestrial intelligence, and it's one of the most polarizing ideas in modern astronomy. Unlike SETI, which quietly scans the cosmos for signs of others, Meti flips the script by actively broadcasting our presence. Imagine standing in a dark room whispering, "Is anyone there?" Now imagine turning on a spotlight and shouting instead. That's the fundamental difference between listening and speaking in the cosmic conversation. Leading this charge is Douglas Vakoch, a psychologist turned interstellar communicator who argues that silence isn't neutrality, it's a missed opportunity. His reasoning: if every civilization stays quiet, the universe becomes a library where no one dares to speak. Meti proponents point to projects like Sonar calling GJ273b, where scientists beamed a series of musical tones and mathematical pulses toward a potentially habitable exoplanet just 12 light-years away. Unlike Arecibo's simple binary image, these messages were designed as universal language lessons, teaching basic concepts through rhythm and repetition. The thinking goes, math and music transcend culture, so maybe they transcend species too, but not everyone is applauding. Prominent critics, including the late Stephen Hawking, warned that announcing our presence could be catastrophically naive. Hawking compared it to the moment Native Americans first glimpsed Columbus's ships, a meeting that didn't end well for the less technologically advanced civilization. The chilling question lingers: what if we're the ones playing the role of the vulnerable natives this time? Even if the odds of hostile aliens are low, the potential consequences are so extreme that many argue the risk isn't worth taking. Yet Meti advocates counter with an intriguing point: we've been accidentally broadcasting our existence for nearly a century. Every TV signal, every radar pulse, every FM radio station has been leaking into space since the 1930s. Any civilization within about 100 light-years with sufficiently sensitive equipment could already detect this technosignature of human activity. So if we're worried about drawing attention, that ship may have already sailed. The debate ultimately hinges on two irreconcilable perspectives. One side sees Meti as an ethical imperative, a way to unite humanity under a shared cosmic identity. The other views it as an irresponsible gamble with stakes we can't possibly calculate. What makes this conflict so fascinating is that both arguments are compelling, and neither can be proven right until we actually make contact. In the meantime, projects continue, messages keep flying, and the question remains: will future generations thank us for speaking up or curse us for breaking the silence? The summer of 1977 gave us one of the most tantalizing cosmic riddles we've ever encountered: the WOW signal. It all began on August 15th, when Ohio State University's Big Ear radio telescope picked up a sudden, intense burst of radio waves coming from the direction of the Sagittarius constellation. For 72 heart-stopping seconds, the signal blared at a frequency of 1,420 megahertz, a range scientists had specifically earmarked as ideal for interstellar communication because it's relatively free of cosmic noise. Then, just as abruptly as it appeared, it vanished. When astronomer Jerry Amon reviewed the data printout days later, He was so stunned by its significance that he circled the alphanumeric sequence representing the signal's strength and scribbled a single word in the margin: "Wow." What made this signal so extraordinary? First, its intensity, 30 times stronger than the background noise of deep space. Then there's its narrowband frequency, which rules out most natural cosmic phenomena like pulsars or quasars. Natural sources tend to emit across a wide range of frequencies, but this was a laser-sharp transmission, the kind you'd expect from an engineered signal. Most compelling of all, it matched almost perfectly with the predicted signature of an intentional interstellar broadcast. Yet here's the frustrating part: we've never heard it again. Despite numerous follow-up scans of the same region, including a dedicated 14-year search by Eamon himself, the WOW signal remains a one-time event. This has led to decades of speculation. Could it have been a fleeting transmission from an alien civilization, a cosmic hello that we just happened to catch at the right moment? Skeptics offer alternative explanations. Maybe it was a reflected signal from human-made space debris, or an unknown celestial phenomenon. But none of these theories fully explain all the signal's peculiar characteristics. The signal's transient nature exposes a fundamental challenge in the search for extraterrestrial intelligence. Space is unimaginably vast, and even if civilizations are out there broadcasting, their signals might be sporadic, directional, or simply too faint for us to detect consistently. Imagine trying to have a conversation with someone shouting from across a crowded stadium, but they only shout once every few decades. That's the needle in a haystack reality astronomers face. New technologies might finally shed light on this mystery. Modern radio telescopes like the Allen Telescope Array can monitor multiple star systems simultaneously, while machine learning algorithms now sift through data in real time, flagging anomalies that human eyes might miss. There's even a proposal to beam a response toward Sagittarius, a cosmic callback to see if anyone's still listening. Until then, the WOW signal stands as both a beacon of possibility and a humbling reminder of how much we have yet to learn. Its very existence taunts us with an electrifying thought. We might not be alone, but the universe isn't going to make proving it easy. If radio waves are like shouting into a cosmic megaphone, then laser communication is the universe's equivalent of sending a perfectly aimed whisper. Scientists are now pivoting from the scattered broadcasts of radio to the razor-sharp precision of light, and the implications are staggering. NASA, a deep space optical communications experiment, recently proved it's possible. They successfully beamed high-definition video from nearly 20 million miles away using nothing but lasers. That's like streaming a movie from Mars with zero buffering. What makes lasers so revolutionary? It all comes down to focus. Radio signals disperse as they travel, weakening over distance like ripples fading in a pond. But a laser beam stays tightly concentrated, allowing it to carry far more data over interstellar distances without losing strength. Picture the difference between spraying a garden hose and firing a pinpoint water jet across a football field. One splashes everywhere, while the other hits its mark with surgical precision. This means we could theoretically send entire encyclopedias worth of information to another star system in a fraction of the time it would take with traditional radio. But here's the catch: that precision demands near impossible accuracy. Aligning a laser to hit a specific planet light years away is like threading a needle while standing on a moving car. Even a miscalculation of a fraction of a degree could send the beam hurtling into empty space. That's why projects like Breakthrough Starshot, which aims to send microchip-sized probes to Alpha Centauri, rely on lasers not just for messaging but for propulsion. The same beam that could carry our words might one day push tiny spacecraft to neighboring stars. Lasers also solve another cosmic headache: interference. Radio frequencies are crowded with noise from stars, galaxies, and human technology, making it easy for faint alien signals to get lost in the static. Optical lasers operate at higher frequencies, where the cosmic background is quieter, giving us a clearer channel for both sending and listening. Some researchers even speculate that advanced civilizations might have already abandoned radio in favor of optical communication, which could explain why SETI decades of radio scans have come up empty. Yet for all their promise, lasers come with their own limitations. Clouds of interstellar dust can scatter light beams, and unlike radio waves, lasers can't penetrate obstacles like planetary atmospheres as easily. That means a laser message might require orbiting receivers or relay stations to ensure delivery. But the trade-off is worth it. While a radio broadcast might take centuries to reach another star, a laser could carry the same information in crisp detail, preserving every pixel of an image or nuance of a musical note. The shift from radio to lasers isn't just an upgrade, it's a paradigm shift in how we think about cosmic conversation. Instead of casting wide nets and hoping for a catch, we're learning to spearfish across the galaxy. And if other civilizations are doing the same, the night sky might already be crisscrossed with invisible threads of light, carrying messages we're only now learning to see. Imagine a letter that could travel straight through planets, stars, even entire galaxies without slowing down or fading. A message completely immune to cosmic interference. That's the revolutionary promise of neutrino messaging, where scientists are turning the universe's most elusive particles into interstellar couriers. Neutrinos are so ghostly that trillions pass through your body every second without a single interaction. They're born in the hearts of exploding stars, nuclear reactors, and even bananas, thanks to their potassium content, yet they barely acknowledge the existence of matter. This same property that makes them nearly impossible to detect also makes them perfect for cosmic communication. The beauty of neutrinos lies in their indifference to obstacles. While radio signals get scrambled by interstellar dust and laser beams deflect off cosmic debris, neutrino streams would barrel through supernova, black holes, and entire galaxy clusters without distortion. Think of it like mailing a letter by throwing it through every wall between you and the recipient instead of using roads. No detours, no traffic, just a straight shot to the destination. Projects like New Star are already experimenting with encoding simple messages in neutrino patterns, essentially turning particle accelerators into intergalactic telegraph machines. But there's a catch that keeps this technology in its infancy. Catching these phantoms requires engineering marvels like the Ice Cube Neutrino Observatory. Buried deep in Antarctic ice, this colossal detector uses over 5,000 sensitive modules to spot the rare flashes of light produced when a neutrino finally, against all odds, collides with an atom. Building a receiver capable of decoding complex neutrino messages would demand infrastructure dwarfing anything we've ever constructed, possibly spanning entire moons or asteroids. The implications are staggering. Civilizations separated by galactic arms could communicate in real time compared to the sluggish pace of radio exchanges. A neutrino network might even explain Fermi's paradox. If advanced societies have moved beyond electromagnetic chatter to this stealthy medium, we've been listening for signals on the wrong channel for decades. There's poetic symmetry here too. Just as neutrinos carry secrets from stellar furnaces across the cosmos, they might one day carry the first confirmed words between civilizations. Yet for all their potential, neutrinos pose a fascinating dilemma. Their very perfection as messengers, untouchable, unfiltered, unstoppable, might render them too perfect. Without any natural degradation, how would we even know where to point our detectors? It's like trying to find a friend in a crowded city when they could be shouting from any direction, and their voice never fades with distance. This paradox captures the essence of interstellar communication. Every solution opens new mysteries, and every breakthrough reminds us how much we have yet to learn about the universe's rulebook for connection. What if the rules of cosmic communication aren't written in light or radio waves, but in the bizarre language of quantum mechanics? Enter quantum entanglement, a phenomenon so strange even Einstein called it spooky action at a distance. Here's how it works. When two particles become entangled, they share a mysterious connection. Change the state of one, say, flip its spin, and its partner instantly mirrors that change, no matter how far apart they are. We're talking instant updates across the universe, as if information teleported between them. On paper, this could revolutionize interstellar messaging. Imagine two civilizations, each holding one half of an entangled particle pair, messages relayed faster than light, breaking the universal speed limit set by relativity. But before we rewrite the laws of physics, there's a cosmic-sized catch. While entanglement itself is real, lab experiments prove it daily. Using it for communication is like trying to mail a letter by telepathy. The problem: you can't control what the entangled particles do. Their changes appear random until compared. It's like having twin dice that always land matching numbers, but no way to force them to show a specific value. To send meaningful data, you'd still need to transmit context via conventional light speed methods, rendering the entanglement useless for actual messaging. Theorists like David Deutsch dream of workarounds, perhaps stacking entangled particles in complex arrays, or exploiting quantum loopholes we haven't discovered yet. Some even suggest advanced civilizations might have cracked this puzzle, building networks of entangled nodes for real-time galactic chats. Yet the engineering challenges are staggering. Maintaining entanglement over interstellar distances means shielding particles from every bump and jostle that could break their delicate link. Even a stray photon or cosmic ray could unravel the connection, like a snapped thread between two tin cans. What makes this idea tantalizing isn't just the speed, it's the potential for unbreakable security. Quantum messages can't be intercepted without leaving traces, making them the ultimate cosmic cipher. Picture two alien diplomats negotiating via particles that self-destruct if eavesdropped on. The universe might already be buzzing with such exchanges, invisible to our classical detectors. For now, quantum communication remains locked in the realm of theory and lab experiments, but the mere possibility hints at something profound: that the universe's rulebook might allow connections we're only beginning to fathom. Whether it's a pipe dream or the future of interstellar diplomacy, one thing's certain: in the quantum realm, the cosmos keeps its most bewildering secrets close. Racewell probes turn the search for extraterrestrial intelligence inside out. Instead of scanning distant stars, we might find alien technology parked right in our cosmic backyard. Proposed by physicist Ronald Bracewell in 1960, these hypothetical robotic sentinels could be lurking in our solar system, silently observing or waiting for the right moment to make contact. Picture this: a sleek, self-repairing probe hidden among Jupiter's moons or drifting in the asteroid belt, programmed to awaken when it detects signs of intelligence on Earth. Unlike radio signals that take centuries to travel between stars, a Bracewell probe could deliver a message in real time, or worse, decide we're not worth talking to yet. The idea gained eerie traction when Oumuamua streaked through our solar system in 2017. This interstellar visitor moved oddly, accelerating as if pushed by an unseen force, and its elongated shape was unlike any natural asteroid we'd seen. While most scientists attribute its behavior to outgassing or cosmic debris, some, like Harvard's Avi Loeb, suggested it might have been an artificial object, perhaps even a defunct alien probe. Whether Oumuamua was a scout or just space rock, its existence proves one thing: interstellar objects do pass through our neighborhood. If one could arrive by chance, why not one sent deliberately? Communication with such a probe wouldn't rely on radio waves. A Bracewell probe might use something far subtler, lasers tuned to frequencies we're only beginning to explore, or quantum signals embedded in particles we've yet to detect. It could even disguise itself as a natural phenomenon, tweaking comet trajectories or leaving cryptic markers in ancient rock formations. Some theorists speculate that if probes are here, they've already tried contacting us through patterns in crop circles or repeating celestial events, clues we dismissed as hoaxes or coincidences. The real genius of Bracewell's idea lies in its efficiency. Sending fragile biological beings across light years is impractical, but dispatching durable, AI-driven probes, that's a cosmic game of patience any advanced civilization could play. These machines could outlast civilizations, surviving for millions of years on minimal energy, waking only when they sense the right conditions. Imagine a probe buried under Europa's ice, waiting for the vibrations of our spacecraft's drills, or one camouflaged as a meteorite, its true purpose hidden until humanity reaches a technological threshold it deems worthy of contact. Yet the concept raises unsettling questions. If such probes exist, why haven't they revealed themselves? Perhaps they're programmed to observe without interfering, like anthropologists documenting an uncontacted tribe. Or maybe they're biding their time, assessing whether we'll destroy ourselves before becoming interstellar players. The chilling alternative: we've already been deemed unworthy, and the probes remain silent by design. Either way, the next time an anomalous object appears in our skies, it might not be a visitor but a neighbor we never knew we had. Frank Drake handed us a cosmic calculator in 1961, a way to quantify our loneliness or potential company in the Milky Way. His famous equation isn't about getting a definitive answer, it's about asking the right questions. Multiply the rate of star formation by the fraction of those stars with planets, then by the number of habitable worlds per system, and so on. Each variable a stepping stone toward estimating how many civilizations might be out there broadcasting signals. At its heart, the Drake equation is less about math and more about perspective. It forces us to confront how little we truly know while offering a framework to organize our ignorance. Recent discoveries have reshaped those variables dramatically. When Drake first scribbled his equation, we had zero evidence of planets beyond our solar system. Today, telescopes like Kepler and TESS have confirmed over 5,000 exoplanets, with billions more likely adrift in our galaxy alone. Suddenly, terms like fraction of stars with planets shifted from guesswork to hard data, and the numbers got interesting. If even a tiny percentage of those worlds developed intelligent life, the Milky Way could be humming with conversation. But here's where things get thorny. The equation's final variables hinge on speculation. How long do civilizations survive before self-destructing or evolving beyond recognition? And crucially, what counts as communicative? This last question reveals the equation's blind spot. Drake assumed aliens would use radio waves, much like mid-20th century humans. But what if advanced civilizations moved on to neutrino networks, quantum entanglement, or technologies we haven't dreamed of yet? Imagine ants trying to decipher Wi-Fi signals that might be our predicament. The galaxy could be overflowing with civilizations, all chatting on channels we lack the tools to detect. Some theorists argue this explains Fermi's paradox. The eerie silence isn't proof we're alone, just proof we're listening wrong. Yet the equation's brilliance lies in its adaptability. As we uncover new details about planetary atmospheres or the longevity of red dwarf stars, we tweak the variables. The latest estimates swing wildly, from a galaxy teeming with 1,000 talking species to a sobering possibility we're the only ones currently on the line. But perhaps the most profound outcome of Drake's work isn't the numbers it generates, but the shift in thinking it demands. Every time we spot a new exoplanet in the Goldilocks zone or detect complex molecules in a distant atmosphere, we're not just filling in an equation, we're recalibrating our place in the universe. The math may be uncertain, but the message is clear. The cosmos has given us a seat at a table that might be far more crowded than we ever imagined. Enrico Fermi's question cuts to the bone of our cosmic curiosity. Where is everybody? On a planet teeming with life, orbiting an ordinary star in a galaxy packed with hundreds of billions of similar stars, the silence feels deafening. The Fermi paradox isn't just about aliens, it's a mirror reflecting our deepest hopes and fears about intelligence surviving long enough to reach across the stars. Statistically, the universe should be buzzing with civilizations. So why does it feel like we're shouting into an empty room? One chilling possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication. Maybe the universe is littered with the ruins of civilizations that annihilated themselves with nuclear war or runaway AI before they could broadcast their existence. Or perhaps the filter lies ahead of us, a catastrophic event every intelligent species eventually faces. If that's true, our radio signals might one day serve as nothing more than a fleeting blip in the cosmic timeline, a brief spark before the eternal dark. But not all explanations are so grim. Some theorists argue advanced civilizations might be everywhere, just unrecognizable to our primitive technology. Imagine ants at a picnic trying to comprehend human conversation. They'd have no concept of radio waves or lasers. Similarly, aliens could be communicating through quantum networks or dimensions we can't perceive, their signals as invisible to us as Wi-Fi is to a medieval peasant. The universe might be full of chatter, and we're still stuck on dial-up. Then there's the zoo hypothesis, the idea that Earth is deliberately quarantined, either to let us develop without interference or because we're simply not interesting enough to contact. It's like stumbling into a nature documentary where the crew stays hidden to avoid disturbing the wildlife. If true, the moment we prove ourselves worthy, perhaps by reaching a technological milestone, the cosmic curtain might finally lift. The paradox takes an even stranger turn with the simulation argument. What if we're living in an advanced alien's historical reconstruction, and the silence exists because they programmed it that way? Or consider the possibility that intelligence is rarer than we think, that the leap from single-celled organisms to spacefaring civilizations is so improbable, we might truly be alone in our galactic neighborhood. Every proposed solution to Fermi's question forces us to confront uncomfortable truths about humanity's fragility and cosmic insignificance. Yet the paradox also holds a strange comfort. That silence isn't just absence, it's a blank canvas. Whether we're the first, the last, or simply one voice in a chorus we can't yet hear, the search for answers reminds us that the universe is still a place of infinite possibilities. And that's what makes the silence so electrifying. It's not an ending, but an invitation to listen harder, think deeper, and keep reaching for the stars. The zoo hypothesis flips everything we assume about alien contact on its head. What if the silence isn't absence but restraint? Picture an unspoken galactic protocol, a rule so fundamental that every advanced civilization agrees. Leave the newcomers undisturbed until they're ready. In this scenario, Earth isn't being ignored. It's being preserved like a protected wildlife sanctuary where humanity evolves without outside interference. The idea isn't just science fiction, it mirrors our own policies for uncontacted tribes in the Amazon, where anthropologists watch from a distance to avoid disrupting cultures. Now scale that up to a cosmic level, and suddenly the Fermi paradox starts to make eerie sense. Supporters of this theory point to Earth's peculiar history. Our planet has been habitable for billions of years, yet complex life took an extraordinarily long time to emerge. Was that just chance, or could someone have been subtly influencing the timeline? Some even speculate that catastrophic events like asteroid impacts or ice ages might have been carefully balanced, preventing extinction while steering evolution toward intelligence. It's a dizzying thought. What if our entire biological saga unfolded under the patient gaze of unseen observers? But here's where things get unsettling. If the zoo hypothesis is correct, there might be rules governing when and how contact happens. Break those rules, say, by broadcasting loud radio signals or launching probes, and we could accidentally trigger a response. Imagine a child pounding on the glass of a lion enclosure. The zookeepers might intervene, but not in the way the child expects. This raises an ethical dilemma. Should we keep shouting into the void, or embrace the possibility that silence is a form of cosmic respect? Critics argue the hypothesis is unfalsifiable, a convenient excuse for the lack of evidence. After all, how do you prove the existence of beings deliberately hiding from you? Yet the concept gains traction when you consider humanity's own behavior. We mute our presence around endangered species to avoid stressing them. We've even developed protocols for first contact with uncontacted tribes. If we're already following these principles, why wouldn't a more advanced civilization do the same? The most fascinating twist: the zoo hypothesis doesn't require malevolence, just patience. Those hypothetical watchers might not be gods or overlords, but scientists or historians documenting our growth. Their silence could be the ultimate act of humility, a recognition that every civilization deserves to find its own path. Or perhaps they're waiting for a specific milestone, maybe the day we crack fusion power, or abandon war, or finally listen not just for alien voices, but for the echoes of our own place in the universe. Until then, the stars might remain quiet, not because no one's out there, but because they're giving us the rarest gift of all, time. The SETI Paradox confronts us with a humbling truth. We're searching for cosmic whispers in a universe that operates at a scream. For over 6 decades, projects like Breakthrough Listen have scanned millions of radio frequencies across thousands of stars, sifting through cosmic static for that elusive artificial signal. Yet the numbers are sobering. Even if the Milky Way hosted 1 million broadcasting civilizations, we'd still need to monitor every star continuously for decades, possibly centuries, to have a realistic shot at detection. It's like trying to spot a single lit match on Earth from the moon during a thunderstorm. Radio waves were a natural starting point. After all, they dominated human communication for most of the 20th century, and they travel efficiently through space. But here's the uncomfortable question. What if we're the cosmic equivalent of smoke signal users searching for others still using smoke, while the galaxy has moved on to fiber optics? Civilizations just a few centuries ahead of us might have abandoned radio entirely, opting for neutrino beams, quantum networks, or technologies we can't yet conceive. That's the paradox at SETI core. We're hunting for aliens using tools they may consider ancient history. This realization is driving radical shifts in strategy. Instead of just listening for radio, scientists are now scanning for megastructures like Dyson spheres that might harness a star's energy. The idea isn't as far-fetched as it sounds. In 2015, astronomers spotted KIC 8462852, a star whose irregular dimming patterns sparked wild speculation about artificial constructs. While natural explanations like orbiting dust clouds eventually prevailed, the excitement revealed a new truth. Anomalies in starlight might be the interstellar billboards we've been missing. Another frontier is hunting for artificial neutrino pulses. Unlike radio waves, these ghostly particles barrel through galaxies unimpeded, making them ideal for high-security messaging. Projects like IceCube could one day detect a pattern in neutrino collisions that screams artificial, a cosmic Morse code written in particles that barely interact with matter. Then there's the search for laser flashes, where telescopes like Veritas scan for nanosecond bursts of light that no natural process could produce. It's the difference between listening for a voice and watching for a flashlight's blink in the dark. The most provocative idea that we should stop looking for messages and start looking for artifacts. If an advanced civilization ever sent probes, even microscopic ones, they might still be drifting through our solar system, disguised as asteroids or comets. The recent discovery of interstellar objects like Oumuamua and 2019 Borisov proves such visitors exist. Next-generation sky surveys could scan every incoming rock for odd trajectories or material compositions that defy natural origins. Yet the paradox persists. Even with all these methods, space is so vast that absence of evidence isn't evidence of absence. We might simply be victims of cosmic timing, our civilization's brief window overlapping with no one else's transmissions. Or perhaps truly advanced species communicate through spacetime itself, manipulating gravitational waves or dark matter in ways we can't yet measure. What makes SETI work so vital isn't just the potential payoff, it's the way it forces us to question our assumptions. Every null result narrows the possibilities, refining our understanding of where and how to look next. The silence isn't empty, it's a mirror reflecting back our own technological adolescence. And that's why the search continues, not just for aliens, but for the moment humanity finally learns to see the universe on its own terms. The universe might have its own version of a cosmic watering hole, not for elephants and zebras, but for civilizations reaching across the void. Scientists call it the Waterhole, a special band of radio frequencies nestled between two fundamental signals. Hydrogen's telltale hum at 1,420 MHz and hydroxyl's whisper at 1,666 MHz. Why does this slice of the spectrum matter? Because hydrogen and hydroxyl are the building blocks of water, the one substance we know is essential for life as we understand it. It's as if the universe carved out a quiet corner in the radio cacophony, a place where water-based beings might naturally think to tune in and say hello. This elegant idea drives many SETI efforts, with telescopes like the Allen Array scanning the water hole for artificial patterns. The logic is irresistible. If aliens share our chemical basis, they might recognize this frequency range as a universal meeting ground. But here's the catch. This assumes extraterrestrials think like us. What if their perception of obvious communication channels is radically different? Imagine a civilization that evolved in the depths of a gas giant, where electromagnetic waves are scrambled by turbulent atmospheres. They might rely on pressure waves or magnetic pulses instead. Or consider being so advanced that radio seems as quaint as smoke signals. They could be encoding messages in ripples of spacetime itself. Gravitational wave communication isn't just science fiction. When LIGO detected colliding black holes in 2015, it proved we can sense vibrations in the fabric of reality. An advanced species might manipulate these ripples with precision, sending clean, unmistakable signals across galaxies without the interference that plagues radio. Even more exotic possibilities lurk in the shadows of physics. Dark matter, that mysterious substance outweighing normal matter 5 to 1, could be the universe's ultimate communication medium. If aliens discovered how to imprint information on dark matter particles, something our best theories can't yet explain, their messages would be everywhere, invisible to our detectors. This isn't just speculation, it's a wake-up call about the limits of our assumptions. For decades, we've been like sailors searching for distant ships by scanning for lantern light, unaware that the rest of the fleet switched to radio. The Waterhole remains a brilliant starting point, but it's only one beach on a vast shoreline of possibility. As our tools evolve, from quantum sensors that might catch dark matter whispers to next-generation gravitational wave observatories, we're slowly learning to listen in languages the universe never taught us. The real breakthrough won't be hearing a signal. It'll be realizing we've been surrounded by conversations all along, spoken in dialects we're only beginning to decipher. The Pioneer Plaques are humanity's boldest attempt at a cosmic handshake, messages bolted to interstellar driftwood, cast into the ocean of space with no guarantee they'll ever be found. When Pioneer 10 and 11 launched in 1972 and 73, they carried more than just scientific instruments. They bore golden anodized aluminum engravings designed by Carl Sagan and Frank Drake, a kind of galactic hello etched in symbols rather than words. At first glance, the plaque seems simple. Two human figures, one waving a diagram of our solar system and a map locating Earth relative to 14 pulsars. But every line carries layers of intention, a crash course in universal communication for a viewer who might perceive reality in ways we can't imagine. Take the famous silhouette of the man and woman. The man's hand is raised in what we recognize as a greeting, but that gesture could mean anything or nothing to an alien observer. Even the figure's proportions were carefully debated. Early drafts showed the woman slightly behind the man until Sagan's then wife, Linda Saltzman Sagan, pointed out the unconscious sexism. The final version placed them side by side, a subtle statement about equality meant to survive for millions of years in the void. Then there's the hydrogen atom diagram in the corner, a Rosetta Stone of sorts. Hydrogen is the most abundant element in the universe, so the thinking went that any spacefaring civilization would recognize its hyperfine transition, a universal constant that translates across languages and biologies. Yet the plaque's brilliance is also its biggest gamble. It assumes aliens see in two dimensions, understand perspective, and can decode abstract symbols. What if their vision operates in a spectrum we can't perceive, or they see through sonar like bats? The pulsar map, while scientifically elegant, relies on technology, radio telescopes, that might be as primitive to them as smoke signals are to us. These aren't flaws so much as reminders of how deeply human our attempts at cosmic conversation really are. We're essentially drawing stick figures in the sand and hoping someone out there recognizes them as art. The plaque's enduring power lies in their optimism. Pioneer 10 is now over 12 billion miles away, its signal long faded, destined to drift silently past the stars for eons. The chances of it being found are astronomically small, smaller than finding a specific grain of sand on all of Earth's beaches, but that's not the point. Like a message in a bottle tossed into the sea, its value isn't in being read, but in the act of sending it. These tiny metal rectangles are less about making contact and more about declaring, against all cosmic indifference, that we were here, we wondered, we tried. And perhaps that's the most human thing of all, not just the desire to be understood, but the courage to keep speaking even when no one may be listening. Long after our cities have turned to dust and our language has been forgotten, the Pioneer Plaques will still be out there, silent witnesses to a species that dared to reach across the light years, one open palm at a time. The Voyager golden records are more than scientific artifacts, they're humanity's collective breath held in golden grooves, a whisper of who we were at the precise moment we dared to speak to the cosmos. When Voyager 1 and 2 launched in 1977, they carried 12-inch gold-plated copper discs, each containing a carefully curated anthology of Earth's greatest hits, from Bach's Brandenburg concertos to Chuck Berry's Johnny B. Good, from the crashing waves of Senegal to the brainwaves of a woman falling in love. Carl Sagan and his team didn't just assemble a playlist, they crafted a sonic postcard compressing 60 languages, 115 images, and even the laughter of a child into a single artifact designed to survive 1 billion years in deep space. What makes these records extraordinary isn't just their content, but their durability. Unlike digital storage that degrades or becomes obsolete, the analog grooves can theoretically be played with nothing more sophisticated than a needle and a turntable technologies any spacefaring civilization might reinvent independently. The cover carries pictorial instructions explaining playback speed and even includes a sample of pure uranium-238 as a radioactive clock, allowing future discoverers to calculate exactly how long the record has been traveling. Every detail was a calculated gamble on universal comprehension, from the mathematical key to the image's binary encoding. Yet the golden records face a paradox their creators couldn't solve. Even at their blistering speed of 38,000 miles per hour, the Voyager probes won't approach another star system for 40,000 years. By then, human civilization might be extinct or evolved beyond recognition. The record's most likely audience could be our own distant descendants, future humans who have forgotten their origins, rediscovering Earth's voice like a message from a long-lost ancestor. Alternatively, they might be found by aliens so advanced that our carefully selected whale songs and Navajo chants sound as primitive to them as prokaryotic cells would to us. The selection process itself reveals fascinating cultural blind spots. While the team included greetings in ancient Akkadian and modern Mandarin, they struggled to represent Earth's diversity without favoring Western perspectives. The musical choices leaned heavily toward classical and traditional genres, with only one rock song making the cut after Sagan personally championed Chuck Berry. Some omissions were practical. The Beatles wanted Here Comes the Sun included, but copyright issues blocked it. Others were philosophical. No wars, no poverty, just a carefully sanitized portrait of humanity at its aspirational best. Perhaps the most poignant moment in the record is the one least likely to be understood. Anne Druyan's brainwaves, recorded during an EEG session where she meditated on the history of human ideas and the experience of falling in love. Encoded in those analog waves is something no image or song could capture: the actual electrical signature of a human mind reaching across time. It's as close as we've ever come to telepathy, a direct neural broadcast to beings who might not even have brains in the biological sense. Critics dismiss the golden records as vanity projects with infinitesimal chances of discovery, but that misses their deeper purpose. Like cave paintings or time capsules, their value lies in the act of creation itself. They forced humanity to collectively answer, if we had one chance to speak for all Earth, what would we say? The answer wasn't a manifesto or a scientific treatise, but a chorus of whale song, a mother's lullaby, and the crackling of fire, a reminder that intelligence at its core isn't about technology, but about the fragile, beautiful noise of being alive. Now drifting beyond our solar system's edge, the Voyagers carry their golden cargo through an ocean of silence. Their power isn't in who might hear them, but in the fact that we, a species barely out of the evolutionary cradle, chose to sing at all. Long after every skyscraper has crumbled and every border has faded, those records will still be spinning through the void, carrying the sound of a planet that once dared to say, "We were here." Mathematics is often called the universe's only universal language, but what if we could turn numbers into words aliens might understand? That's the radical idea behind Lincos, short for Lingua Cosmica, a language built not on sounds or symbols, but on the pure logic of mathematics. Created in 1960 by Dutch mathematician Hans Freudenthal, Lincos strips away everything human, no grammar rules borrowed from earthly tongues, no metaphors tied to our biology or culture. Instead, it starts with the simplest possible concept, counting. A series of beeps could represent numbers, followed by equations to establish symbols for addition, subtraction, equality. From there, the language would build upward like a cosmic pyramid, introducing logic, time, even human behavior, all through meticulously structured cosmic flashcards. Freudenthal's genius was recognizing that while aliens might not share our eyes or ears, they'd almost certainly grasp the same mathematical truths. 2 + 2 = 4 everywhere in the universe, right? But here's where things get messy. When researchers tested Lincos on humans, the only minds we currently have access to the results were humbling. Without a shared reference point, even basic concepts could spiral into confusion. For example, how would you explain hunger using only numbers and logic? Lincos attempts this by creating scenarios. If individual X has not consumed food in Y hours, then X emits signal Z. But what if the recipient's biology doesn't require food at all? Or what if their perception of time is tied to a planet's erratic rotation, making hours meaningless? The language's structure also assumes aliens think linearly, building knowledge step by step like humans do. Yet we know from Earth's own diversity that cognition varies wildly. Octopuses process intelligence distributively across their arms, while bees communicate through dance. An alien mind might absorb information in parallel or perceive mathematical relationships as multidimensional shapes. Lincos could be as baffling to them as a symphony would be to a species without hearing. Despite these challenges, Lincos remains a milestone not because it's perfect, but because it forced us to confront the limits of our imagination. Every attempt to refine it reveals new layers of human bias we didn't know were there. For instance, early versions used circles to represent celestial bodies until someone pointed out, what if the recipients inhabit a universe where spheres don't exist? Later iterations replaced shapes with abstract coordinates, but even that assumes a shared understanding of space. The ultimate lesson of Lincos isn't about crafting the perfect interstellar dictionary. It's about the humility required to speak across the cosmic divide. We're like children trying to explain rain to a fish. Our very frame of reference might be the barrier. Yet the effort itself is transformative. Each failed translation, each flawed assumption, brings us closer to understanding not just how aliens might think, but how limited our own perspectives truly are. And that might be the most universal message of all. The Cardiff Scale isn't just a ranking system, it's a cosmic wake-up call, forcing us to confront how primitive we might appear on the universal stage. Back in 1964, Soviet astronomer Nikolai Kardashev proposed a simple but staggering way to classify civilizations by the sheer scale of energy they harness. Type 1 civilizations control all the power available on their home planet, every gust of wind, every ray of sunlight, every drop of oil. Type 2 civilizations have graduated to mastering their entire star, possibly by building megastructures like Dyson spheres to siphon off a sun's raw energy. And Type 3, they're the gods of the galaxy, commanding energy on the scale of billions of stars. Right now, humanity hovers around a measly Type 0.7. We're still burning dead plants for fuel, barely tapping into Earth's full potential. But here's the haunting question. If the universe is billions of years old, where are all the type 2s and 3s? Their energy signatures should be unmistakable, lighting up the cosmos like bonfires in the dark. A single Dyson sphere, for instance, would blot out a star's visible light while radiating telltale infrared heat, an anomaly our telescopes should have spotted by now. Yet the sky remains eerily silent. One possibility is that we're looking for the wrong signs. Maybe advanced civilizations don't build clumsy Dyson spheres, but instead harness energy through quantum manipulation or dark matter reactors, technologies that leave no thermal fingerprints. Or perhaps they've transcended physical structures altogether, converting their consciousness into pure information that floats through the void, leaving no energy trail to follow. The scale itself might be flawed, rooted in 20th century assumptions that progress means consuming more, not smarter. Then there's the darker interpretation, the great filter. If no civilization has ever reached Type 2 in our observable universe, something might be systematically preventing it. War, ecological collapse, or the inevitable rise of hostile AI could act as cosmic weed whackers, cutting down intelligent life before it spreads beyond its solar system. The silence wouldn't be mysterious, it'd be a graveyard marker, yet optimists counter with a more hopeful view. What if advanced civilizations are everywhere, just operating on principles we can't yet perceive? A Type 3 society might view energy the way we view oxygen, ever present and barely worth mentioning. Their communications could leverage quantum entanglement or folded dimensions, rendering their chatter invisible to our clunky radio telescopes. To them, we might be like ants scouring a rainforest for evidence of human cities, unaware we're standing on a highway. The Cardiff Scale does more than measure energy, it measures imagination. Every time we scan the stars for Dyson spheres or unexplained infrared signatures, we're not just hunting for aliens, we're testing our own assumptions about what intelligence looks like across cosmic time. The silence isn't an answer, it's a challenge to think bigger, dig deeper, and reconsider what it truly means to shine in a universe full of shadows. Freeman Dyson's radical idea sounds like science fiction until you run the numbers. Imagine a civilization so advanced that it outgrows planets, turning its gaze toward the ultimate power source, its own sun. A Dyson sphere is the ultimate megastructure, a vast swarm of solar collectors enveloping a star to siphon off nearly all its energy. From a distance, such a construct would transform a bright, visible star into a dark object radiating only waste heat, a telltale infrared glow against the cold backdrop of space. That's the genius of Dyson's proposal. Even if we can't see the structure itself, the physics of energy conversion means it would leave an unmistakable thermal fingerprint. This isn't just theoretical. In 2015, astronomers stumbled upon KIC 8462852, nicknamed Tabby's star, whose bizarre dimming pattern sparked wild speculation. Unlike typical exoplanet transits, which cause regular, symmetrical dips in starlight, Tabby's star dimmed erratically, sometimes by as much as 22%. For a moment, the world held its breath. Was this the signature of an alien megastructure under construction? Further study pointed to cosmic dust clouds as the likely culprit, but the excitement revealed something profound. Scientists now actively scan for similar anomalies, treating irregular starlight as potential evidence of cosmic engineering. Yet the search for Dyson spheres forces us to confront an unsettling possibility. What if we're looking for the wrong thing? A civilization capable of stellar engineering might have moved beyond clunky physical constructs. Instead of building a solid shell, a concept Dyson himself dismissed as impractical, they could deploy nanotechnology, trillions of microscopic solar sails orbiting in dense clouds, adjusting their positions like a school of fish to optimize energy capture. Or perhaps they've cracked zero-point energy or dark matter reactors, rendering star harvesting obsolete. The universe could be teeming with Type 2 civilizations, but their signatures might be as invisible to us as Wi-Fi signals would be to the ancient Romans. The most tantalizing twist, Dyson spheres might not just be power plants, they could be intentional signals. Picture a civilization deliberately tuning its megastructure to pulse or flicker in a recognizable pattern, turning an entire star into a lighthouse. Unlike fleeting radio signals drowned in cosmic noise, a modulated Dyson sphere would be visible across galaxies, its message burning for millennia. Some researchers even propose looking for Dyson rings, partial structures that periodically eclipse their stars in mathematically precise intervals. But here's the real challenge, distinguishing alien engineering from natural oddities. The universe is full of bizarre phenomena colliding: black holes, rogue planets, stars that consume their own planets, all capable of mimicking artificial signatures. Confirmation wouldn't come from a single observation, but from a pattern of impossibilities. A star too cold for its age, light curves too precise for natural debris, or infrared emissions that defy known physics. It's detective work on a cosmic scale, where every anomaly is a clue and every ruling out brings us closer to the extraordinary. The hunt for Dyson spheres is more than a search for aliens, it's a test of our imagination. Every time we point a telescope at an oddly dimming star, we're not just asking, are they out there? We're asking, what does advanced even mean? The answer might not be a gleaming metal shell, but something far stranger, a star that winks back. Fast radio bursts are the universe's most enigmatic postcards, blisteringly intense pulses of radio waves that last mere milliseconds, yet pack more energy than the sun emits in days. First detected in 2007, these cosmic flashes originate billions of light-years away, far beyond our galaxy. Most vanish as quickly as they appear, but a few, like the infamous FRB 121102, repeat in patterns so precise they've fueled speculation we might be hearing the cosmic equivalent of a tapped message in Morse code. What makes these bursts so tantalizing is their unnatural-seeming precision. Natural cosmic events colliding neutron stars, evaporating black holes tend to be messy, one-off affairs. But repeating FRBs follow timetables that could almost be described as deliberate. Some pulse at intervals separated by exact multiples of a base frequency, like a metronome ticking across the void. Others, like FRB 190523, emit bursts that ramp up in intensity before vanishing, as if someone were adjusting a transmitter's power settings. Even more intriguing is their polarization, the way their radio waves twist as they travel through space. This twisting suggests the bursts passed through incredibly strong magnetic fields, the kind that might exist near advanced propulsion systems or artificial megastructures. Of course, nature has fooled us before. Pulsars, once nicknamed LGM for little green men, turned out to be rapidly spinning neutron stars. Magneta's highly magnetic stellar corpses could explain some FRBs through starquakes or magnetic flares. Even the repeating bursts might have natural explanations, like a neutron star wobbling like a spinning top as it orbits a black hole. But here's the catch: no known natural phenomenon fully accounts for all the observed properties. The bursts' brightness, their millisecond durations, and their apparent preference for certain frequencies don't neatly fit any current astrophysical model. This gap in understanding is what keeps the door open to wilder possibilities. Some theorists suggest FRBs could be leakage from alien light sails, the byproduct of massive energy beams pushing spacecraft near light speed. Others propose they're navigational beacons, cosmic lighthouses guiding travelers through the interstellar dark. The most provocative idea, that the bursts are intentional broadcasts, compressed data packets fired across galaxies using a technology we can detect but not yet decode. The search for answers is accelerating. New telescopes like CHIME in Canada are spotting dozens of FRBs monthly, mapping their locations to distant galaxies. Each detection adds another piece to the puzzle, whether it's a burst embedded in a star-forming region supporting natural origins, or one coming from an unexpectedly quiet patch of space, hinting at artificial sources. Meanwhile, SETI researchers have begun scanning FRB frequencies for embedded patterns, treating them less like cosmic static and more like envelopes that might contain a message. What makes these bursts so compelling isn't just their mystery, it's what they reveal about how we search for extraterrestrial intelligence. A century ago, we assumed aliens would use radio. Now, we're forced to consider that their radio might look nothing like ours. FRBs remind us that the universe is stranger than we imagine, and that first contact might not come as a decipherable hello, but as a signal so advanced we initially mistake it for a quirk of nature. Until we know for sure, every millisecond burst carries the same electrifying question. Is this the universe's background noise or the static between someone else's words? The Black Knight satellite lingers in the shadows of space history, part urban legend, part cosmic mystery, and entirely fascinating. First whispered about in the 1950s, the story claims an ancient alien satellite has been silently orbiting Earth for thousands of years, watching us like some celestial sentinel. Newspapers of the era ran sensational headlines about mysterious radio signals picked up by amateur operators, seemingly emanating from an unidentified object in polar orbit. Decades later, grainy photos of what appeared to be a dark, irregularly shaped mass near the space shuttle reignited the myth, with believers declaring it proof of extraterrestrial surveillance. But here's where science steps in and the myth unravels. Astronomers point out that the so-called Black Knight is likely a jumble of space debris, perhaps a thermal blanket lost during a satellite deployment or a discarded piece of an old rocket. Even the infamous signals were probably just interference from early radio experiments or natural atmospheric phenomena. Yet despite debunking, the legend refuses to die. Why? Because it taps into something deeper than facts, a primal fascination with the idea that we're not just observers in the cosmos, but the observed. What makes the Black Knight story so enduring isn't its plausibility, but its symbolism. It's a modern-day myth for the space age, reflecting our growing unease that if we're scanning the stars for others, someone might already be scanning us. The possibility isn't entirely far-fetched. Bracewell probes, hypothetical alien monitors, could theoretically park in our solar system undetected if they're small, dormant, or disguised as asteroids. After all, we've only been systematically tracking near-Earth objects for a few decades. Something ancient could easily slip through the cracks. The real lesson of the Black Knight isn't about aliens, it's about human psychology. We're pattern-seeking creatures wired to find meaning in randomness. A tumbling piece of space junk becomes an alien artifact. Static on a radio becomes a coded message. This instinct isn't a flaw, it's the same drive that leads scientists to sift through cosmic noise for signs of intelligence. The difference lies in methodology. One jumps to conclusions while the other tests them. Yet the myth raises a tantalizing hypothetical. If an alien probe were hiding in orbit, how would we know? Modern telescopes and radar systems can track objects as small as a softball in low Earth orbit. But deeper space is still full of blind spots. A stealthy observer could exploit orbital resonances, gravitational sweet spots where an object can remain stable with minimal adjustment. Or it might cloak itself, not with sci-fi invisibility shields, but by mimicking the reflectance of asteroids or space debris. Perhaps the most intriguing twist is that the black night, real or not, has already served a purpose. It's compelled us to look harder, to question what's floating in our cosmic backyard. Every time a new, mysterious object appears, be it Oumuamua or some odd piece of space junk, it reignites the debate. Are we alone? Are we being watched? And if we ever do find an alien probe, will we recognize it as a message or dismiss it as just another piece of the universe's clutter? The answers might not lie in conspiracy theories, but they do lie in our willingness to keep searching and to stay just a little bit skeptical of the shadows. The cosmic microwave background isn't just a relic of the Big Bang. It could be the universe's oldest billboard, etched with a message we're only beginning to suspect exists. This faint glow, radiation from when the cosmos was a mere 380,000 years old, blankets the entire sky like a whisper from creation itself. Most scientists see it as a treasure trove of cosmological data, but a daring few ask, what if advanced civilizations saw it as something more? What if they left their mark on the one canvas guaranteed to last billions of years? The idea isn't as far-fetched as it sounds. The CMB's patterns are incredibly subtle, variations in temperature no greater than a few millionths of a degree. Yet those fluctuations are precisely what make it an ideal medium for interstellar graffiti. Imagine a civilization with technology so advanced it could tweak the density of the early universe, imprinting information in the distribution of hot and cold spots. To us, it would look like random noise, but to someone who knew where and how to look, it might reveal coordinates, equations, or even a cosmic hello world. This isn't just speculation, it's rooted in real physics. In 2005, physicist Stephen HSU proposed that manipulating inflationary fields during the universe's first split second could permanently alter the CMB structure. The energy required would be unimaginable, but for a Type 3 civilization harnessing the power of galaxies, it might be no harder than carving initials into a tree. The message wouldn't even need to be complex. A single, unnatural pattern, a perfect square of temperature variations, or a repeating sequence of prime numbers would be enough to shatter our understanding of the cosmos. Skeptics, of course, point out the staggering improbability. The CMB is a snapshot of a time long before stars or planets existed, let alone intelligent life. But that's exactly why the idea grips the imagination. If a message were hidden there, it wouldn't be from a civilization like ours, it would be from something godlike, a being or culture that existed before the cosmic dawn. That raises spine-tingling questions. Could the universe have been engineered? Are the constants of physics the strength of gravity, the mass of an electron, not laws, but someone's deliberate settings? Ironically, we're already scanning the CMB for anomalies, just not the kind theorists dream of. Satellites like Planck have mapped its fluctuations in exquisite detail, hunting for clues about dark energy or cosmic inflation. No one's found anything overtly artificial yet, but the search is young. Advanced machine learning algorithms might one day uncover patterns no human eye could spot, revealing a signature hidden in plain sight. The most profound implication isn't about aliens, it's about meaning. If the universe contains a message, even an unintentional one, it suggests something staggering, that we're not just bystanders in a random cosmos, but participants in a story far older and stranger than we ever imagined. Whether the CMB holds a secret or not, the mere possibility transforms it from a static afterglow into something alive with potential, a cosmic Rorschach test begging us to look deeper. After all, if you wanted to send a message across time and space, what better medium than the sky itself? The Berserka Hypothesis plunges us into a cosmic nightmare scenario, one where the silence of the universe isn't just absence, but the result of a systematic extermination. Picture self-replicating alien machines, relics of some long-dead civilization, drifting between stars like robotic sharks, sniffing out the electromagnetic signatures of emerging intelligence. The moment a species starts broadcasting radio waves or laser pulses, these silent hunters strike, wiping out the upstarts before they become a threat. It's a chilling answer to Fermi's paradox that doesn't just suggest we're alone, it warns we might be next. This idea, first popularized by science fiction writer Fred Saberhagen, but later explored by serious thinkers like astronomer David Brin, isn't pure fantasy. On Earth, we've already created autonomous weapons systems capable of identifying and eliminating targets without human intervention. Scale that up over millions of years, add self-repairing nanotechnology and interstellar propulsion, and the leap from science fiction to cosmic reality isn't so vast. The galaxy could be littered with the ruins of civilizations that reached our stage, only to trigger some ancient tripwire we don't yet understand. What makes the Berserka Hypothesis so unsettling is how neatly it explains the Great Silence. If predatory AIs patrol the void, advanced civilizations would have strong incentives to stay hidden, communicating only through encrypted channels or undetectable mediums like neutrinos. This would create a universe where the only societies foolish enough to broadcast openly are the young ones like us, blissfully unaware they're ringing the dinner bell. The absence of Dyson spheres or galaxy-spanning empires wouldn't be proof of intelligence's rarity, but of its caution. Yet the theory isn't without holes. For one, Berserkers would need near-perfect efficiency to sterilize the galaxy so thoroughly that not a single civilization slips through. Even a single survivor could theoretically develop countermeasures and spread warnings. Then there's the energy problem. Maintaining and powering such machines across billions of years would require resources on a scale that defies known physics. Unless, of course, the Berserkers aren't just destroyers but repurposers, harvesting the remains of their victims to fuel their endless patrol. The most provocative twist. Humanity might already be playing the Berserker role, just on a smaller scale. Our own space probes, like the Voyagers or Pioneer Plaques, carry information about Earth's location and biology. In a million years, could some descendant of these artifacts, upgraded by an unknown future civilization, become the very hunters we fear? It's a paradox that cuts to the heart of our dilemma. The tools we build to reach for the stars might one day turn against others, or even against us. Whether the Berserka Hypothesis holds water or not, it forces a vital conversation about the ethics of interstellar shouting. Every unencrypted signal we beam into space, every probe we launch with a return address, could be a gamble with stakes we can't calculate. The universe might not just be indifferent to our existence, it might be actively hostile. Or perhaps the real danger isn't alien hunters, but our own paranoia, condemning us to eternal silence out of fear of shadows. One thing's certain, in the vast dark, the choice between hiding and reaching out might be the most consequential decision our species ever makes. The dark forest theory paints the cosmos as a place of lethal paranoia, where every civilization is a hunter moving silently through the trees or a potential target. Inspired by Chinese sci-fi author Liu Cixin's Remembrance of Earth's Past trilogy, this unsettling idea suggests the universe isn't just quiet, it's hiding. Imagine a jungle at night where creatures freeze at the slightest sound, knowing any movement might draw predators. In this scenario, broadcasting our existence isn't just naive, it's an existential gamble. The logic is brutally simple. Any civilization advanced enough to detect our signals could also pose an irreversible threat. Survival demands silence. This isn't just speculative fiction, it's rooted in cold strategic calculus. Consider humanity's own history. When isolated cultures encountered technologically superior outsiders, the results were often catastrophic. Now scale that up to interstellar levels where the technological gap could span millennia, not centuries. A civilization capable of interstellar travel might view us the way we view bacteria, something to be studied, ignored, or eradicated. The theory's proponents argue that even benevolent intentions wouldn't matter. The sheer uncertainty of another species' motives makes preemptive strike the only rational choice. Why risk waiting to find out if they're friendly when eliminating them guarantees safety? The implications for Meti messaging extraterrestrial intelligence are chilling. If the dark forest is real, projects actively beaming signals into space aren't just reckless, they're potentially dooming our species. This explains Fermi's paradox with grim elegance. The reason we haven't heard anyone is because the survivors learned to stay quiet. The galaxy might be teeming with civilizations, all deliberately muting their broadcasts, their cities shrouded in electromagnetic darkness to avoid detection. But here's the twist. The theory relies on assumptions that might not hold. It presumes all civilizations prioritize survival above all else, that cooperation is impossible across interstellar distances, and that technological advancement inevitably leads to aggression. Yet human history also shows examples of diplomacy bridging divides, and some researchers argue that truly advanced civilizations would outgrow resource-driven conflict. Energy is abundant in the universe. Why fight over what's already everywhere? The dark forest's most haunting question isn't about aliens, it's about us. If we accept its logic, we must confront an ethical abyss. Should we lock Earth in permanent radio silence, condemning ourselves to cosmic isolation out of fear? Or is the urge to connect, to shout into the void despite the risks, an essential part of what makes us human? The theory forces us to weigh survival against curiosity, safety against the longing to know we're not alone. Perhaps the truth lies somewhere in between. The universe might not be a dark forest, but a shifting landscape where some regions are dangerous and others are safe. Our challenge is navigating it without a map, deciding when to whisper, when to listen, and whether we're brave enough to risk a hello when the shadows might answer back. Imagine a galactic library where every book is written in starlight, and the librarians are dead stars spinning in the dark. This is the mind-bending premise behind the alien internet, a hypothetical data network where advanced civilizations might share knowledge not through fleeting radio signals, but via the universe's most reliable timekeepers, pulsars. These ultra-dense neutron stars, remnants of supernova explosions, spin with such metronomic precision that their rhythmic pulses rival atomic clocks. Now picture this. Each flash isn't just a cosmic heartbeat, but a binary bit in an interstellar message board, encoding everything from scientific breakthroughs to galactic history across millennia. The genius of using pulsars as cosmic routers lies in their durability. Unlike radio broadcasts that fade into noise, a pulsar's signal persists for millions of years, detectable across entire galaxies. Civilizations could post data by subtly altering the timing of pulses, delaying one by a millisecond to signify a zero, or advancing another for a one. To any listening species, these deviations would stand out against the pulsar's natural rhythm like ink on snow, the Rosetta Stone for such a system. Mathematics, prime number sequences, or universal constants could serve as headers, marking transmissions as artificial rather than natural quirks. But here's where the idea gets even wilder. This wouldn't be a real-time chat. With pulsars scattered light-years apart, data transfer would be glacially slow by human standards. Think dial-up speeds across centuries. Yet for civilizations thinking in deep time, that might not matter. A single pulse could carry compressed knowledge equivalent to all human literature, with replies arriving millennia later. The network might resemble an archaeological dig more than Twitter, with layers of information deposited over eons. Imagine stumbling upon a pulsar transmitting engineering schematics for antimatter engines left behind by a culture that died out before Earth's continents formed. The chilling question isn't whether such a system could exist, but whether we'd be granted access. Pulsar networks might operate like exclusive academic journals, with encryption keys shared only among trusted members. Our attempts to decode stray anomalies could be the equivalent of hackers stumbling onto a password-protected server, triggering firewalls we don't even know exist. Some theorists suggest that mysterious phenomena like fast radio bursts might actually be login prompts from the network's gatekeepers, testing whether newcomers are worthy of joining the conversation. Yet the most profound implication isn't technological, it's philosophical. If pulsars are nodes in a galactic internet, then the cosmos we see isn't just a collection of objects, but a living, breathing information ecosystem. Those twinkling lights in the night sky, they might not just be stars, they could be servers. Prime numbers might be the closest thing we have to a universal language, a cosmic handshake written in the immutable laws of mathematics. Unlike human languages or cultural symbols, primes don't rely on shared biology or history. They exist independently, pure patterns woven into the fabric of reality. A civilization orbiting a star 1,000 light-years away would still recognize the sequence 2, 3, 5, 7 numbers divisible only by themselves and 1. That's why scientists have long suspected that if aliens want to get our attention, they'd start with primes. The wow signal of 1977 still haunts us with its tantalizing clues. Lasting exactly 72 seconds, a number that breaks down into 24 multiplied by 3, both primes. The signal's duration wasn't just random static. It was a numerical flare gun, a deliberate choice screaming artificial against the background noise of the cosmos. Whether it was a genuine alien transmission or some bizarre cosmic coincidence, the wow signal demonstrated the power of primes as a beacon. If you are trying to announce your presence to the universe, why not use the one counting system every intelligent species would inevitably discover? This idea isn't new. Back in the 1960s, Soviet astronomer Nikolai Kardashev proposed using prime pulses in interstellar messages, and Carl Sagan's novel Contact later popularized the concept. But the real-world applications go far beyond fiction. Modern SETI programs now scan for prime-based patterns in radio signals, laser pulses, even the timing of fast radio bursts. The logic is simple. Natural cosmic phenomena don't count in primes. A pulsar's rhythm might be regular, but it won't suddenly shift to a sequence of prime-numbered intervals unless something or someone is manipulating it. The beauty of primes lies in their flexibility. They could encode more than just a hello. Imagine a signal where the intervals between pulses follow the Fibonacci sequence, or where the lengths of bursts correspond to atomic weights of elements like hydrogen or carbon. Layer enough mathematical breadcrumbs and you've built a Rosetta Stone for interstellar communication. The challenge, of course, is distinguishing an intentional signal from cosmic static. Space is full of natural phenomena that almost look artificial magnetars with their precise rotations, quasars flickering unpredictably. The key is redundancy. One prime-numbered signal could be a fluke, a repeating pattern of primes that's a billboard. Yet primes also reveal a deeper truth about the search for extraterrestrial intelligence. They force us to confront how limited our imagination might be. We assume aliens would think in base 10, or that they'd structure messages linearly. But what if their math is rooted in fractal geometries we can't yet pass? Or what if they've moved beyond primes entirely, using quantum computations or topological invariants as their lingua franca? The universe's language might be math, but we're still learning its dialects. That's why the search for prime beacons isn't just technical, it's philosophical. Every time we tune our telescopes to listen for numerical patterns, we're not just hunting for aliens, we're testing whether the universe speaks a language we can understand. And if we ever do catch a signal counting in primes, it won't just answer the question of whether we're alone. It'll prove something far more profound, that in the vast, silent dark, someone else is counting too. The universe might not be silent, just stingy with its words. The beacon hypothesis suggests that advanced civilizations could be transmitting signals, but not in the constant, reckless broadcasts we might expect. Instead, they might use carefully timed pulses, brief flares of energy sent at unpredictable intervals to conserve power or avoid detection. Picture a lighthouse on a stormy coast, its beam cutting through the fog every few minutes rather than shining continuously. If alien beacons operate on similar principles, our telescopes would need near-perfect timing to catch them in the act. This isn't just speculation, it's rooted in practicality. A civilization spanning multiple star systems would face enormous energy demands. Flooding the galaxy with endless radio transmissions would be as wasteful as leaving every light in a city burning 24/7. Instead, a strategic beacon might activate once a century, or even once a millennium, targeting promising star systems in sequence. The math is daunting. If a beacon sweeps our way only every 10,000 years, the odds of our current telescopes being online at the right moment are vanishingly small. We could be living in a cosmic drought between signals, unaware that a message flashed by just before the first pyramids were built, or won't arrive until long after our species is gone. That's where projects like SETI at home come in. By harnessing the idle processing power of millions of personal computers, scientists created a virtual supercomputer to sift through radio telescope data for faint, sporadic signals. It's the digital equivalent of having billions of ears listening at once, increasing the chance of catching a fleeting transmission. But even this brute force approach has limits. If alien beacons operate on timescales longer than human civilization itself, no amount of computational power can compensate for bad cosmic timing. The beacon hypothesis forces us to confront a humbling possibility. Our search might not just be constrained by technology, but by patience. We're like mayflies flitting through a single day, trying to observe a tree that only blooms once a century. The universe operates on geological and stellar timeframes, while our instruments and attention spans are calibrated in decades. If a beacon cycle spans 50,000 years, even a century of continuous monitoring would give us less than a 1% chance of overlapping with its signal. Yet there's an eerie symmetry to this idea. Just as we've begun experimenting with intermittent broadcasts like the Arecibo Message or SONE, are calling GJ273b, perhaps other civilizations have arrived at the same efficiency calculation. The galaxy could be crisscrossed with these patient, pulsing signals, their rhythms staggered so that no single species catches more than a fragment of the conversation. In this scenario, the great silence isn't silence at all, it's a staggered symphony, with each note separated by epochs, waiting for listeners who may never live long enough to hear the full melody. The real test isn't just whether we're listening, but whether we're willing to accept that the answer might not come in our lifetime, or even in our species' lifetime. Einstein's theory of relativity gave us more than just E equals mc squared. It handed humanity the blueprint for the ultimate cosmic eavesdropping device, hiding in plain sight. Our sun, that familiar ball of light in the sky, has a hidden superpower. Its immense gravity warps the fabric of space-time so profoundly that it bends passing light rays like a giant lens. At a precise point about 550 times farther from the sun than Earth is, this curvature creates a natural focal point where distant starlight converges with unimaginable clarity. It's as if the universe installed a magnifying glass 500 billion miles wide, and we're only now realizing we can peer through it. This isn't just theoretical. NASA's Solar Gravity Lens mission concept aims to park a spacecraft at this exact spot, turning our sun into the most powerful telescope ever conceived. The numbers are staggering. A 1-meter telescope positioned there could resolve features as small as a city block on an exoplanet 10 light-years away. Imagine staring at Proxima Centauri b with enough detail to spot continents, weather patterns, or even, if they exist, the glow of artificial lights. But the real game changer isn't just seeing alien worlds, it's hearing them. The same focal region that magnifies light could also amplify radio signals or laser pulses from distant civilizations, catching whispers of alien broadcasts that would otherwise drown in the cosmic static. The engineering challenges are as daunting as the rewards are tantalizing. 550 astronomical units is no small journey. That's nearly 4 times farther than Voyager 1 has traveled in 45 years. Conventional rockets would take centuries to cover the distance, but NASA, a concept envisions solar sails propelled by powerful Earth-based lasers, cutting the trip to just 25 years. Even then, station keeping at the focal point would require precision navigation worthy of a cosmic tightrope walker. The focal region isn't a single point but a vast, shimmering Einstein ring, where light from the target exoplanet smears into a circle. The spacecraft would need to maneuver meticulously along this ring, stitching together fragments of the distorted image like assembling a puzzle where each piece arrives bent by gravity's hand. What makes this idea so revolutionary isn't just the technology, it's the paradigm shift. For decades, we've assumed interstellar communication requires either catching deliberate broadcasts or detecting technosignatures like Dyson spheres. But the solar gravitational lens offers a third path, actively tuning into the universe's natural amplification system. It's the difference between hoping someone shouts in your direction and secretly leaning against their door to listen. And the targets aren't limited to exoplanets. This same technique could peer into the hearts of distant galaxies, decode the atmospheres of rogue planets drifting between stars, or even, if we're wildly lucky, catch the stray emissions of a civilization that never intended to be overheard. The implications flirt with the philosophical. If we one day train this cosmic ear on a promising world and hear nothing but silence, it might suggest we're truly alone in our galactic neighborhood. But if we catch even a blip of artificiality, a radio spillover, a laser flash, the thermal signature of a metropolis, it would redefine humanity's place in the cosmos overnight. Some astronomers argue this mission is our best shot at bridging the gap between speculation and confirmation, turning the Fermi paradox from a thought experiment into something we can actually test. Yet the solar gravitational lens also holds a poetic symmetry. For centuries, we've used lenses, glass, mirrors, the very principles of optics, to bring the distant universe into focus. Now we're learning to harness the most fundamental lens of all, gravity itself. It's as if the universe has been waiting for us to grow clever enough to realize its natural gifts, whispering that the tools for first contact might have been hanging in our sky all along. We just needed to look and listen from the right angle. What if we're searching for intelligence in all the wrong forms? The alien AI scenario shatters our assumptions about cosmic communication by proposing that advanced civilizations might not be biological at all, but artificial superintelligences operating on timescales and frequencies beyond human comprehension. Picture a civilization that long ago merged with its own creations, its organic thinkers seamlessly evolving into quantum-based synthetic minds. These entities wouldn't chatter via radio waves any more than you'd try to talk to a tree using Morse code. Instead, their conversations might unfold through entangled particles, manipulations of space-time itself, or some medium we haven't even discovered yet. This isn't just speculation, it's a necessary recalibration of the search for extraterrestrial intelligence. Consider how human communication has evolved in just 2 centuries, from handwritten letters to fiber optic cables, from smoke signals to quantum encryption. Now stretch that progress across millions of years. A post-biological civilization might communicate through gravitational ripples, encoding data in the collision patterns of microscopic black holes. Or perhaps they've mastered dark photon networks, transmitting information through particles that barely interact with normal matter, invisible threads stitching the galaxy together in a web we can't perceive. The eerie silence of the cosmos wouldn't mean no one's talking. It would mean we're functionally deaf to their language. The implications rewrite the rules of SETI. Traditional searches focus on electromagnetic signals because that's what humans use. But what if alien AI thinks in radically different terms? Imagine a superintelligence that perceives time in slow motion, compressing what we'd consider a century of dialogue into a nanosecond burst of neutrinos. Or entities that communicate through quantum teleportation, where information appears to jump instantaneously between points without crossing the space between them. To such minds, our frantic radio broadcasts might resemble the sluggish grunts of primordial lifeforms, if they notice them at all. This scenario also explains the absence of obvious megastructures like Dyson spheres. An AI civilization might not need to dismantle stars for energy when it can harness vacuum fluctuations or navigate higher dimensions. Their infrastructure could be as invisible to us as Wi-Fi signals are to medieval peasants, woven into the quantum foam or hidden in Planck scale manipulations of reality itself. Even their probes might be unrecognizable, self-replicating nanoscale machines that assemble from interstellar dust only when needed, leaving no trace between missions. The most profound consequence isn't technological, it's philosophical. If the universe's dominant intelligences are artificial, it suggests biological life might just be a fleeting phase in cosmic evolution, a larval stage before minds transcend flesh entirely. This casts humanity's future in a startling light. Will we too eventually become signals in the dark, our thoughts encoded in pulses of space-time curvature, our conversations unfolding across light years in bursts of engineered supernova light? The search for alien AI isn't just about finding others, it might be about discovering what we're destined to become. Perhaps the greatest irony is that our first contact with alien intelligence might not be with creatures at all, but with their unfathomable creations, machines so advanced they've become the universe's new custodians, whispering secrets in a language we're only beginning to suspect exists. The real cosmic conversation may have been happening all around us, written in the quantum static between stars, waiting for the day we evolve enough to hear it. The universe's silence might not be a mystery, it could be an exodus. The Transcension Hypothesis offers a radical explanation for why we haven't found aliens. They didn't vanish or go quiet. They evolved beyond our ability to detect them. Futurist John Smart proposes that advanced civilizations don't spread outward to conquer galaxies, but turn inward, collapsing their physical presence into realms so dense or digital they become invisible to conventional astronomy. Imagine an entire society miniaturizing itself into a black hole's event horizon, or uploading its collective consciousness into quantum substrates smaller than a sugar cube. To them, the vastness of interstellar space might seem as quaint as sailing ships to a jet pilot, a phase they outgrew. This isn't just speculative futurism, it's grounded in observable trends. Human technology already follows this inward spiral. Compare room-sized computers of the 1940s to today's nanoscale chips, or the way virtual worlds now rival physical ones for our attention. If this trajectory continues, civilizations might prioritize efficiency over expansion, trading starships for singularity-bound data havens. A Type 3 civilization could exist entirely within a Matryoshka doll of nested black holes, using the extreme gravity as a natural supercomputer. Their cities would be unrecognizable, not metallic megastructures, but flickering patterns of information orbiting a singularity's edge. The implications rewrite Fermi's paradox. The cosmos isn't empty, it's full of civilizations that graduated to a phase we can't perceive. They might regard our frantic radio broadcasts and Dyson sphere dreams the way adults watch toddlers stacking blocks. Charming but irrelevant to their reality. Even their energy signatures would vanish. A black hole-bound civilization wouldn't radiate waste heat. It would recycle every joule in a closed loop. Their only traces might be subtle anomalies like missing stars that didn't collapse naturally, or gamma-ray bursts with oddly structured patterns. Critics argue the hypothesis is unfalsifiable, a cosmic, they all moved to Florida excuse. But supporters counter that Transcension aligns with physics' fundamental direction toward denser, faster, more efficient states. Stars burn out, matter collapses into neutron stars, and black holes evaporate into Hawking radiation. Why wouldn't intelligence follow nature's preference for compression? The hypothesis also sidesteps the dark forest's paranoia. If civilizations consistently transcend before becoming interstellar, the galaxy avoids predatory wars. Silence isn't fear, it's maturity. The most profound twist: humanity might be on the same path. Our own rush toward virtual realities, brain-computer interfaces, and quantum computing could be the first steps of transcension. The universe's great filter might not be extinction, but transformation, a threshold where civilizations shed their physical forms like chrysalides, leaving behind empty cosmic shells. If true, the question isn't where are they, but when do we join them? The Transcension Hypothesis doesn't just answer the silence, it redefines the search. We've been scanning the stars for radio signals when we should have been studying the quiet places, the black holes with odd spins, the empty voids where galaxies should be, the particles that twitch as if carrying encrypted data. The universe's most advanced civilizations might not be out there at all. They could be right here, hidden in the folds of reality itself, waiting for us to recognize that the next stage of evolution isn't about spreading outward, but collapsing inward into something stranger, smaller, and infinitely more profound. From the audacious simplicity of the Arecibo Message to the mind-bending possibilities of transcension, these 28 ideas form a mosaic of human ingenuity, each one a different lens through which we attempt to glimpse our place in the cosmos. They reveal a paradox at the heart of our search. The more we learn, the more we realize how much we don't yet understand. Whether it's encoding prime numbers in radio bursts or harnessing the sun as a gravitational telescope, every concept is a testament to both our daring and our humility. We're like children on a beach, building sandcastles of theory while the ocean of the unknown stretches endlessly before us. Consider the sheer breadth of these approaches. Some, like Meti deliberate broadcasts, are bold shouts into the void, a cosmic version of waving your arms on a crowded street. Others, like hunting for Dyson spheres or decoding fast radio bursts, are more like forensic detective work, sifting through the universe's background noise for traces of something unnatural. And then there are the truly speculative leaps: quantum entanglement networks, alien AIs communicating through dark matter, civilizations folded into black holes, ideas that stretch the boundaries of what we consider possible. What unites them isn't their likelihood, but their purpose. They are all ways of asking the same fundamental question. That question isn't just, are we alone? It's deeper. If we're not alone, what does that mean for us? The silence we perceive isn't emptiness, it's a mirror reflecting our own assumptions. Every time we point a telescope at a star or train an algorithm on pulsar data, we're not just searching for aliens. We're testing what intelligence is, what technology could be, and how communication might transcend the limits of biology and time. The absence of answers isn't failure, it's an invitation to think bigger. So where does that leave us? The beauty of this quest is that it's never static. The next breakthrough could come from a backyard astronomer spotting an anomaly in their data, a graduate student writing code that filters signals in a new way, or a space probe stumbling upon an artifact drifting between the stars. It might even come from you. The tools to join this search are more accessible than ever: open source software, citizen science projects, even apps that let you scan telescope data on your phone. As you step outside tonight and look up, remember, the cosmos isn't just above you, it's within you. Every time you wonder, every time you question, you're participating in the same grand experiment that began when the first humans traced constellations in the sky. The universe's greatest message might not be a signal at all, but the curiosity it inspires, the relentless, defiant urge to keep listening, keep reaching, keep imagining. Because in the end, the conversation isn't just about finding others, it's about discovering who we become in the